Hello and welcome to a special episode of GNSI Speaker Series. My name is Heather and I'm here with the Global and National Security Institute at the University of South Florida. I'm here at the Great Power Competition Summit, and this summit's theme is on AI and strategic competition. Today, we'll be speaking with a few PhD candidates about their research. All right, so you just got done presenting your research. Did you want to start by telling me your name and then a little bit more about your research now?
Of course. So my name is Nicolas Bustos. I'm from the Department of Industrial Engineering here at USF. I'm a PhD student. And I just finished presenting this research that we're working with Marissa, Dr. Layuan, Dr. Sarka, and Dr. Tapasdas. So we're improving the performance of image translator in the literature that is called cycle GAN. And we're using the Fourier transform frequency for leveraging the performance of the model while predicting or generating images that are thermal and they come from RGB images. So this is the main structure of the generative adversarial network. It's basically two networks working in an adversarial way or adversarial network that are aiming to fool each other and well, especially the generator is aiming to fool the discriminator that at the same time is scrutinizing whether an image is real or not. So our method is improving the loss for that particular network by using the frequency domain. The frequency domain captures more details about the outlines and also other frequencies that are computed within the images. And as you can see here, we can improve the performance of the translation by using even more discriminators in our architecture. So we're using two more discriminators that are discriminator and scrutinizing whether an image is real in the frequency domain as well. As you can see here in the first row, we have real thermal images. All the cars here are in a dark brightness of pixel brightness. And then underneath the cars, you see that it's brighter because they have higher temperature that is captured by the thermal camera. So that's the feature we're looking for here. And only using cycle GAN, we get results that are colorizing the image in the grayscale. It's still darkening the sky, the trees, but you see the cars, they don't have really a predominant configuration or characteristics as in real thermal images. Whereas using more discriminators, you can see that cars have been darkened and then the bottom has been brighter, and that works better for representing real thermal images, right? So we tested our models in faster RTNN, which is an object detector. And as you can see here, using more discriminators for the Fourier transform domain leverages the performance of the model from 66% to 72%. So that's a big improvement. We're looking for further improve these models by using a better fine-tune of our hyperparameters. But at the same time, having more discriminators makes the model less flexible, so we can have images that are translated poorly because they don't come from the same features of the train set. And our train set is really daytime clear images, right? So those are the main takeaways that I explain here in my poster. And the future work is really further improving the performance by using more images in the train set, as well as fine-tuning the hyperparameters of our model.
Sounds really interesting. Can you tell me a little bit more about the applications of your research in the fields of computer vision?
Okay, so the applications here is really, you can give an interpretation for that for your work, but we're aiming to augment data sets. So by having just a low amount of real thermal images and a good amount of synthetic images, we can further improve the performance of models because we have more training, we have more data for the training. And also we can use that for fusion algorithms. Fusion algorithms, they aim to create images that come from multi-modal spectrums. And for example, we can merge the information of RGB images and thermal images to compute a better image for tests such as object detection or image segmentation.
Thank you again for telling us about your research, and good luck on your future research.
Thank you.
You just got done presenting on stage. Could you remind me of your name and then tell me a little bit more about your research?
Absolutely. My name is Stephen Steinley. I'm a PhD student at the University of South Florida, Department of Computer Science and Engineering. What we're looking at here today is an application of cognitive modeling in multi-factor authentication. Essentially, the gist is we can use what you have in your head, your cognitive traits, in order to predict who you are from a crowd of people. We can use this to augment security just in case you forget your password or you lose your credentials, don't have access to biometrics, something like that. Now, this is an open area of research, so there's still a lot of questions to be answered. And I'm certainly not claiming that I know everything about the human mind and cognitive model. But what we can use here is the semantic fluency task in order to understand more about a person. We provide them with this task, and then when they provide their answer, we can generate certain inferences about their cognitive traits. Once we get their cognitive traits, we can then provide them with a battery of additional tasks. The semantic fluency task is not by itself enough to identify a person. However, if we can augment that with their tolerance for risk, or possibly even the speed at which they speak, or galvanic skin response, that's how much you sweat, we can then upload all of those into a security system. This security system will ideally be able to find individual traits that most uniquely identify the person. For example, most people in the world, when prompted with the word cat, will respond with the word dog. So that's not enough to determine if somebody is themselves. However, if we provide them with a memory task and also a gambling task, for instance, for risk tolerance, we can use those in aggregate to determine, to do multi-factor authentication. Once we get all of those data points loaded into the system, we can then challenge the user with this task. So once again, imagine that you're logging into your computer and you forget to bring your access card. Instead of having to go talk to your boss and explain why you forgot your access card, you can instead ask the machine to prompt you with a series of tasks, the same series of tasks that you did on your initial battery. This battery of tasks will then authenticate you, or unfortunately, possibly, disallow you from access, depending on how close your original answers were to the answers that you provided when you were prompted. This is an area of open research, so there's a lot of questions that we still haven't answered. We don't know exactly which cognitive traits are most identifying for a user, and also we need to identify more semantic fluency-like tasks to get that cross validation.
What can the semantic fluency task tell us about a person's cognitive traits?
Awesome, well, thank you for asking that question. So the semantic fluency task is the beating heart of this whole process. It's where our research started, and it's where I plan on growing the research from. I have to give credit to my colleague Animesh Nagaskar for his foundational research in semantic fluency task. So if we look at this list down here, we can see that somebody has generated, in response to the keyword animals, dog, cat, mouse, rat, snake, lizard. From this list, we don't really care about the words. We don't care if they say rat or mouse as far as the word goes. What we're looking at is how close are these words semantically related. For example, dog, cat, mouse are all pets. However, mouse and rat are rodents. You can see that mouse belongs to both pets and rodents. This shift here between pets and rodents is something that is used in nature for scavenging and exploitation. For instance, if you were a hungry person several thousand years ago, you might eat an orange from a tree. But if you want more oranges, you're not going to immediately move to a different tree. You're going to utilize all the oranges on that tree before moving on. So in a similar manner, you explore your entire cognitive space, well, your semantic space for a word, before moving on. And this pattern is unique to all individuals. For instance, I might only stay in pets for 2 words before switching over to farm animals, which can both be pets or food depending on how they're utilized. There are many more cognitive traits that we can pull from this exact list. For instance, how many words can you say before you start repeating words? Maybe you only get 3 words in before you say cat again, but maybe somebody else gets through 10 before they start repeating. All of these things can be brought together for multi-factor authentication.
Thank you so much for sharing your research, and good luck in the future.
Awesome, thank you.
So you just got done presenting on stage. Could you remind us of your name and then tell us a little bit more about your research?
Sure. My name's Dr. Paul Hungler. I'm an associate professor at Queen's University in Canada, and my research is on developing intelligent, dynamically adaptive simulations. So this one is directly related to medical trauma team simulations. So what we have is basically we created a bunch of trauma simulations. So if you can imagine a physician going into a trauma situation, having to deal with that. What we're trying to do and what our research is really focused on is looking at how we can get to competency-based assessment quicker. So get those competencies for medical professionals faster. And so in the trauma situation, what we're trying to do is try and get you to a spot where we give you individual training. So individual training for each physician in this area. And how we do that is to try and get it so that we're looking at assessing or classifying your cognitive load as well as your level of expertise through machine learning, and then trying to get that personalized simulation and personalized training from that. So what we did was brought trauma team leads into a trauma environment. They're looking at, as you can see up here, we have a typical medical mannequin. So, you know, they're pretty rudimentary. You can look at them, but they're not that sense of reality. So the trauma team physician has a Microsoft HoloLens, so they're getting augmented reality. So there's a holographic overlay that goes over top of this mannequin, which you can see right here. So that holographic overlay is what you're looking at. So they get really authentic and realistic version of this trauma situation. And for this one, this is a blunt force trauma situation. So they're seeing that, and while they're actually in the environment, we're collecting a bunch of data. So we're looking at ECG, as well as eye tracking, EEG, so looking at brain signals, as well as functional near infrared. So trying to get a lot of different information in real time and collect that data that we can use to assess their cognitive load, as well as their level of expertise. So we get all that data in real time. We synthesize it, we bring it into our machine learning model, create a model that allows us to dynamically adapt that. So if we have a really novice physician, say somebody in medical school, they're in there, they're having a difficult time with the simulation, we can dial it back in terms of difficulty and how quickly we give them the information, take it down a bit, and then build them back up, scaffold it back up. And it's because we're trying to get this really perfect area where you have the most amount of learning that goes on. So we're really trying to change the difficulty and adapt it in real time to your cognitive load so that you can get this maximal outcome for it.
Oh, that's awesome. And how does your research relate to training and education?
So it's really focused on training education. Like I said, what we're really trying to get is that personalized aspect. So every individual, because right now what we do for most training is everybody goes into the same training environment. They go from the start to the finish of a training simulation, and everybody gets the same experience. But for this, with machine learning, we're able to give you your individual personalized. So your data, your cognitive load, your expertise is brought into here, and then we're able to get that. So we've done it here for medical trauma training, but really it can be applied to anything. Military training, pilot training, any of those types of things, to really make it personalized training so that we get the output or the output of it much faster.
That sounds awesome. Thank you so much for sharing your research, and we look forward to your future research.
Thank you.
So you just finished presenting on stage. Could you please remind us of your name and then tell us a little bit more about your research?
Of course, my name is Mersa Mashhedi. I'm a PhD student at the University of South Florida. I'm at the Industrial Engineering Department of this university, and my major research is on computer vision and artificial intelligence. Yeah, of course. So I want to tell you a little bit about my research. So what we wanted to do here was to see the impact of using synthetic data in object detection algorithms. So the first thing is that we did a thorough literature review and saw that different object detection algorithms, they are claiming these performance metrics, but each one of them had evaluated their object detection algorithm on a self-collected custom data set. And therefore, we cannot compare these algorithms to one another. That's the first motivation that we get to this actually research. The other thing is that we have visible images, RGB images that have their own features, and we have thermal images, which we have like other benefits, and we can get other benefits from them. For example, in the darkness, in the RGB image, you cannot like see the cars or people very brightly, but in thermal images, because in thermal images we get heat, the people or the cars are like more visible, more obvious. So what we are doing is having an original image. For example, in this part we have the RGB image. After that, we are generating a thermal image using CycleGAN, and then we are fusing these two different modalities to have a better image, to take advantage of the benefit of the RGB domain and thermal domain as well. So we are analyzing two different object detection algorithms, which is YOLO V7 and FastR CNN, and at the end we are trying to compare the results of them based on different weathers, hours, and based on different sizes. As you can see, we have large objects and small objects.
That sounds really interesting. And what can you tell us about the performance of object detection algorithms in different types of weather?
Okay, so what we have here in the dataset that we are using, which by the name is FLIR, we have clear weather and partly cloudy weather. And we have two different hours for each weather, which is daytime and nighttime. At the beginning, I want to say that we are saying that in this particular dataset, FastR CNN is working better than YOLO V7. And the other thing is that we are seeing a really big gap when we are having daytime images or nighttime images. For example, the MAP, which is the mean average precision, for day images is 0.8, which is good for large objects. But for nighttime images, it would go down to 0.1, which is a really, really low number. And it shows that we have a very big problem here. Another thing that I want to emphasize is that one thing is that daytime or nighttime, another thing is the size of the object, so the large objects and the small objects. In large objects, we have 0.8 here, as you can see, but the same weather, the same hour, when we are going to a small objects, the number would be reduced to 0.06. So we can say that the state-of-the-art object detection algorithms does not perform whether in the nighttime images when the things are not that obvious, or whether for small objects.
Thank you so much for sharing your research, and good luck with your future research.
Thank you so much. Thank you.